All right, so now that we've introduced the idea of loop rule and junction rule and gone through them, we're going to see how we can start applying them onto very complex circuits. All right, so here's what we're going to do. I'm going to start by drawing out a complex circuit. We're going to start off with a relatively simple one. I'm going to have 3 resistors total. And I'm going to give you the following information. I'm going to hook this up with, let's say, a 9-volt battery. And let's call this one resistor A. And resistor A is going to have a value of, let's go 45, let's go 25 ohms. All right. And then I'm going to have resistor B. Let's say that it is 40 ohms. And resistor C, which is going to be, let's go with, I'm trying to make some relatively good numbers here. Let's go with, let's call it 40 ohms as well. Let's just see what we come up with on that. We'll keep it relatively simple, even though this is a complex circuit. All right, here's what I'm going to introduce. Now, many times with some of the circuits I'm going to throw at you so that you can get a lot of practice with this, it gets easy to be overwhelmed by everything, all the bits of information that you may have. So here's what we're going to do. I'm going to introduce our table. Now, whenever we worked with complex problems where there's a lot of information to keep track of, we usually try to keep it orderly. This is just an extension of that. So here's what we're going to do. We're going to put down information for the total circuit. We're going to have resistor A, resistor B, and resistor C. Okay, so I'm going to make a table that looks like this. Now that I've got my table, I like to put total at the top. Some of my older videos has total at the bottom, but we kept running into problems with people just adding stuff up, which is not what you want to do. So table. We're going to need 2 vertical lines here. And what I like to do is at the top, I write delta V equals I, our current, R. It's Ohm's law. It's been a little while since we last looked at Ohm's law, but it still applies. But it applies for each of the individual resistors. Now, the problem that I see students running into a lot is they'll take the full 9 volts and they'll say, okay, there's 9 volts and my resistance is 40 ohms, so I take 9 divided by 40 and I get, well, the current must be 0.225. That's not what you want to do. As we saw, the total height here is 9 volts. This is going to drop us down by a little bit, and this is going to drop us down by a little bit. And so it's not the full 9 volts that is the potential drop, the potential difference across this resistor. And that's where the table starts coming in handy. The idea behind the table is any horizontal row, so any row, you can apply Ohm's law across. So for instance, we know that the total potential difference for the circuit is that of the battery. It is 9 volts, so I'm going to write that in. In fact, after you make your table, start filling in things that you know. We also know the resistance of resistor A is 25 ohms. We know that the resistance of resistor B is 40 ohms, and that resistor C is 40 ohms. Now, with the information I've given you here, that's all we know. So, we need to start going through and figuring out what we could do. Now, I will say this. If we had 2 pieces of information in a row, we could use Ohm's law to solve for the third. Now, many of you may want to take the 9 volts and say that that's delta V and that our resistance is 25, but I cannot stress this enough. Take a look at what we saw before. 9 volts is the total. That is not going to be the drop across this one resistor because there are other resistors after it. We can't go up a height of 9 meters, go down 9 meters, and then have non-existent hills that are also hills. Now, if we had one resistor off by itself, it might actually end up with the full 9 volts, but we do know that we have to apply loop rule onto this. Now, right now, while we could apply loop rule, it's not going to get us very far because we only know one potential difference. And we know none of the currents, so we can't apply junction rule. The nice thing about the table is this. No matter what I ask you for, if you're filling in the table, you're making progress, even if you don't know the end goal. Complex circuits can get really tough because you don't know how to go from one thing to what you're looking for. Well, if you're using the table, as long as you're filling things in, you're making progress. Now, other things that I want to bring up. The table, horizontally, we can apply Ohm's law. But we don't have enough information in this one and many others to actually solve anything. So there are actually 3 tricks. Trick number 1 is for delta V. We can move vertically, we can fill in information vertically in the delta V, our blue column, by using loop rule. That's one of our tricks. We can fill things in vertically in our current column by using junction rule. Now, neither of those are going to help us very much because we don't really have much in the lines of information. So there's one last one. There's a trick for the resistance column, and we've looked at it a little while back. It's equivalent resistance. Great. So I know the resistance of each of these individual resistors. I want to find the total resistance of the entire circuit. Well, we know how to do that. We find our smallest part of the circuit. That's here, these two in parallel. So I would have 1 over 40 ohms plus 1 over 40 ohms equals 1 over my equivalent resistance. Don't forget, 1 over the equivalent resistance, not the equivalent resistance. Well, this is 2 over 40 ohms, which means our equivalent resistance would be equal to 20 ohms. If I were to redraw that, it would look a little something like this. These two that are in parallel, I have replaced with one imaginary one, an equivalent resistor that is 20 ohms, and we know that this one is 25 ohms. Both of these are in series, so I add them directly together, and we get, collapsing this back down to our simple circuit that we know how to work with, we get the following. 45 ohms, and we've got a 9-volt battery. Great. The important thing is we now know the total resistance of our circuit. That's when we get it down to just one equivalent resistor that takes the place of the entire circuit. That's our total resistance, which means I can fill this in. 45 ohms is our total equivalent resistance. We can take values that we have in the resistance column and find other values by looking at equivalent resistance. Great. Now that I've got that, I've got 2 things filled in the top row. I can apply Ohm's law on that row. That's the upside of the table. Any row you can apply Ohm's law on, but you cannot take a value from this row and use a value from the other row. Everything has to be in the row if you want to use Ohm's law. So I take 9 volts divided by 45 ohms, and I end up with my total current through the circuit is 0.2 amps. That means that we've got 0.2 amps coming out of the battery. That's our total current for our circuit. Great, now what do we do? Well, we could apply loop rule, but we haven't actually filled anything in here, so we're going to have a bunch of unknowns. I'm going to keep us on task here, but if you don't know, feel free to write it out. It turns out we're going to need that information later. Now, here's where I like to bring up that small thing that I mentioned, that junction rule doesn't just apply when you have a branch. It technically means any given point. So I have 0.2 amp coming here, but I also have to have the same thing going out. We can quickly, and this takes a little bit of practice to get used to, it's like anything else, the more practice you get, the faster you get. Since we have 0.2 amps coming out of the battery, and it goes this way, all of it must go through resistor A, 0.2 amp. And it continues going over here until it meets this actual real junction, which is a branch off. But like I said, junction rule is actually a statement of conservation of charge. My charges have to go somewhere. Whatever comes in here has to go out, which means if 0.2 amps are coming out of the battery, they're going right into RA. Great. Then they're going to split. Some of them go this way and some of them go this way, and I don't know how much. So you might be able to jump to some conclusions based on things we've talked about before, but we're going to show you the thorough way. But now that I've filled this in, you'll see, hey, I've got 2 more things in RA. I can apply Ohm's law. So 0.2 times 25 ohms, applying Ohm's law, my current times my resistance, gives me my potential difference, which is 5 volts. Great. Okay, unfortunately, now I'm a little stuck. Now my junction rule, I'll go ahead and mention what hopefully you're thinking. Well, it's 40 ohms over here, 40 ohms over here. I made a big deal about how the current will split up based on how hard it is to get through any of the stuff. Since it's equally hard to get through both sides, the current is actually going to split in half. Probably 0.1 is going that way and 0.1 is going that way. Now that being said, While that's a perfectly safe way to go about it, assuming you're thinking correctly mathematically, I'm going to show you the more thorough way. But we've got an idea of what it should be. Let's apply some loop rule. Here's what I'm going to do. I'm going to go around my circuit. I'm going to start on the far end of the battery like I like. I go across the battery, and the battery gives me plus 9 volts. I keep going. I go across RA. We said that RA takes away 5 volts. It lowers us down by 5 volts. And then we go over here. Now here's where the loop rule comes in. I can choose one side. I'm going to choose to go over to B. I go across B minus delta VB. I have no idea what that is, but that's okay. I keep going, and lo and behold, I end up back where I started, which means all of this must add to 0. 9 minus 5 is 4. Minus delta VB is 0, so we find delta VB must be equal to 4 volts by Kirchhoff's loop rule. 4 volts. Great. And now I've filled out something else so I can go in and apply Ohm's law. 4 volts equals my current times 40 ohms, my resistance. So I'm going to take 4 volts divided by 40 ohms. And to no one's great surprise, I get 0.1 amp, which is half of the current. It does match up with what we predicted. But just in case you look at this and we have maybe square root of 3 as our resistance here and 147 over here, you can't really do that in your head. So I try and teach you the thorough way so that you can always solve any of these problems. Great. Now we could either do loop rule again, going across the battery and go the other way, or we could also keep in mind what I mentioned before, that if this has a potential drop of 4 volts, then another branch must also have, for the total branch, the same drop of 4 volts. Or we could also say the following. We have 0.2 amp coming in, 0.2 amp coming in, 0.1 goes this way. So for Kirchhoff's junction rule, we have to have 0.1 go this way, because if we have 0.2 coming in, 0.1 going that way, we must have 0.1 going the other way. All of these are great ways to come up with the exact same answer. When we multiply these across, no matter which way you do it, you're going to end up with the same answer filling in here. This is what I like about the table, because it gives us a great idea of what's going on. And it allows us to navigate complex circuits. Now this is one with only 3 resistors. I've been known to give questions with 5 or 6 resistors in all sorts of combinations. Now there's one last thing that I'll bring up. I'm going to follow up with one final question, and it's been a while since we've seen it. What's happening with the power in our circuit? Okay, well, as a brief reminder, P equals IV. Now, I usually put this on the last area here next to the table, but I do not make it part of the table itself, because the table shows you where you can multiply out for Ohm's law. So I'm going to find the total power of my circuit, and I can do that by taking I times delta V, P I delta V. So 0.2 times 9, I end up with the total power of the circuit is 1.8 watts. Take a look at the previous videos in case you're wondering where I came up with that. Oh, I wrote PIV, PI delta V. Okay, and if I do this, I'd have 0.2 times 5, 0.2 times 5. I end up with 1 watt is being used by resistor A. And let's see, 0.1 times 4 volts, that's 0.4 watts for resistor B. And 0.1 times 4 volts, hey, it's going to be the same for the other, 0.4 watts. Now, for those of you who were wondering about conservation of energy, specifically, because remember I said potential differences are related to energy, but they're not energy itself. But since they're related, it's because of conservation of energy that loop rule works out. But for those of you who think, well, if the battery's supplying 9 volts, how do we have 5 plus 4 plus 4? That's what, 8 plus 5? That's 13. That doesn't add up. That's because volts are not energy. They're just heights. Power is energy per time. And what this is saying is every second, the battery is releasing 1.8 joules. And every second, resistor A is using 1 joule, and every second, resistor B is using 0.4, and resistor C is using 0.4 joules. Every second. The battery is giving out 1.8 joules, and these resistors, this one is taking away 1 joule per second, This is taking away 0.4 joules, and this is taking away 0.4 joules. When we add all of these up, we see that they come up to 0. The total energy that is being put out by the battery that we keep track of in the power. Every second, this battery would release 1.8 joules, and each of the resistors takes up some of that. Sorry about that, my phone just chimed at me. Turns out I ran out of space on my storage drive. That's okay, switched over to the other drive, and we'll finish this up. As I was saying, this is where energy conservation is actually showing. What the battery is putting out, it raises things up to a height of 9 volts, but the actual energy it's putting out is that height, 9 volts, multiplied by the charges going through it, represented by the current. Just like I said before with loop rule, the ski lift takes everyone up by a height of 30 meters, but the amount of energy it gives depends on how heavy the people are. Depends on the current that you have going through there. The battery is putting out 1.8 joules every second, and each of the resistors total is now using up that total energy. All of the energy is being used up in our circuit, and we're not creating energy and we're not destroying energy. As I said, loop rule is not exactly energy, but it's based off of energy, and it works.